Hi, today we'll discuss about mass moment of inertia and the area moment of inertia. My name is Julapot Jirawasharadet. This lecture is a part of a course in engineering mechanics at International Program in Civil Engineering, King Mongkut University of Technology, Thonburi. Thank you for being here with us and hope you enjoy the time with us. Firstly, I'd like to discuss about the moment of inertia, this term here. As I already said, there are mass moment of inertia and the area moment of inertia. The word inertia is usually something that against a motion. So if the mass moment of inertia is the inertia that go against any changes in body rotational state or rotational speed, basically. If it's the area moment of inertia, it will be inertia against any change in the area rotational state. Maybe it's resistant to the rotation of the area itself. And this is why, as an engineer, we have to learn this feature. Similar to the mass resist of the acceleration, the mass moment of inertia will resist the rotational change as well. First, look at the mass moment of inertia. Imagine the whole body in this blue color, right? If you want to know the mass moment of inertia of it, we'll start from a small element of this mass, which we call dm, the lowercase m, right? If we look at the top view, this mass is rotating about z-axis as we draw it. If we look at the top view here, we'll see that the mass actually moving in this small mass, moving in a circle, right, with the radius r. This r is already constant for this little mass. However, this r will change according to the position of every mass. If it's closer, r will become smaller. If it's further away from the rotational center, then r will be longer, depending on the small mass dm. However, we assume that at the moment, at this stop moment, it has a constant angular acceleration of alpha. Of course, if it rotates in a circle, right, there will be two force or two directional movement that we will be looking at it. One is on the tangent line. In this case, we will talk about the force on the tangent line, the small force called Ft, and the one that actually pull it into the center of the circle, which keep it changing direction into a circular motion. That is the Fn, or the small one on the small mass is the Fn. The one we'll be looking at is the acceleration, the force that acting on the tangent line, the small dft, because that is the one that changes the speed, right? So if we already know that the force is equal to the mass times acceleration, right? But in this case, it's not any acceleration because we're talking about only the force in the tangent direction, so it's the acceleration in the tangent direction as well. So that's the equation, and we know that the moment, right? The moment that actually caused by the small ft is the small ft times the arm length. In this case, is the radius. So basically, the moment that acting on this body here would equal to the radius times the force, the ft, right? And we already have solution for the ft, so we expand it into the equation, right? The capital M is the moment, the lowercase m is the mass, right? And we already know the relationship between the acceleration in the tangent line and the angular acceleration. This is, I think, you learned it in physics, I think, right? So we can use the expression and substitute into the expression of that small moment. And of course, if we want the whole moment acting on the whole body, then we have to integrate that expression, right? And we already said that the angular acceleration alpha is a constant, so we will take alpha outside the integration. Now notice the format of equation, right? You have the term of force, right? In this case, moment, right? And then you have the term of acceleration. In this case, because moment is angular, so acceleration here is angular acceleration alpha, right? And we have the what we call the mass property, right? The integration of r squared dm, compared to the expression we know, F equal to ma, right? F is a force A is acceleration. Since F is a force in a line, A therefore is an acceleration in a line, and M itself is a property of mass, right? So this one is the same comparison. Moment is a rotational force, and alpha is angular acceleration, and then of course property of mass. Therefore, if we talk in a term, then we would like to have a term which what's called we create a term so that we understand something like mass, but in this case it's mass moment of inertia, which will come from the term integration of r squared dm, the small mass, all over the area of mass itself, right? Usually sometimes it's called I and then the subscript capital G, right, to signify the fact that it's a mass, but in this case we just use I for now. Let's talk about the area moment of inertia, which will be the main focus on this lecture here, right? The mass moment of inertia will be used more in dynamics, right? So this one here will be, but this one will be concerned, and the way we calculate is similar anyhow, right? So let's look at this area. You see that little block there below there, right? That is a representation of an area, right? This area is subject to a pressure force, right? This is with the force basically, right? It's very linearly with the y-axis, okay? And it's also becomes zero at the point of rotation that we are looking at. In this case, if we look at the side view, we'll probably see this picture, right? And because this is straight line function, right, vary now with y, so straight line function with the height of p, therefore p equal to a constant c times y, right? So that's the idea, and what we now want to do is take moment about point O. So let's look at the equation, right? So if we say that there is a small force, right, causing at the representation there of dA, right, that small force dF will equal to the pressure itself times the area, right? The pressure P, in this case we use lowercase p, times the small area there, which is dA, right? So now, as I said, we want to take the moment. Then of course, it's the moment about point O, about x-axis through point O, right? So we need to find the arm. So let's go back to the side view again. So this is the side view, right? So basically you see now we have the arm at that position of P, the arm is actually Y, right? So therefore the moment, the little moment called the MO is equal to the arm times the force y dF, which of course dF equal to P dA, so we substitute it to get the last expression. Then we already discussed this. This is a linear function. P is linearly with y, and P is 0 at y equal to 0. Straight line function is a term of the height of the graph is equal to a constant times the distance you measure, right? So it's P equal to C times y. Substitute in the expression we already have. We have that. And then if we want to create the whole moment, then we integrate the whole expression with total area, right? Again, we come MO times C, which is a constant, take out of the integration, and then we left with integration of y squared dA all over A, right? And that is the term we call the area moment of inertia. But notice this one here is Ix, which means it's the area moment of inertia about x-axis, though. We'll discuss in further detail later. Okay, so that's the idea. Notice that both mass moment of inertia and area moment of inertia evolve about moment and rotational stages. One is for mass, so it's about the whole body rotating. And the area moment, therefore, is about the area rotating, right? So it depends on what we are looking at. As I mentioned before, we will focus more in area moment of inertia from this point onward. Okay, I'd like to discuss a little bit more about the associated content with this content, meaning what you need to know. First, what you need to know when you actually want to study about or calculation about the area moment of inertia or mass moment of inertia, right? So the one that you need to know first is the center of mass and gravity, and of course the positions of the centroid. This will become more apparent later, but this is the one that you need before you move on forward. Okay. Secondly, I want to talk about why we learn it, right? Okay, we already talked about is inertia, that resisting moment, or basically resisting rotation, right? The first topic would be about the angular acceleration and direction of an object that you need to calculate in your dynamics, right? In your and many other applications later on. And of course, in terms of the static and up to the structural analysis part, it will be involved with the stress and deformation that caused by torsion, meaning twisting an object, right? Of course, twisting means turning, right? It's a moment there. And the next one will be stress and deformation caused by bending moment, right? The bending moment actually causes rotation in the cross-sectional area, right? We will talk in detail later. And then the stress actually caused by shear force, because it's actually, well, it's not so obvious, but the stress caused by shear force is actually solved and proved from the stress causing by bending moment. Therefore, the area moment of the shear will come into play as well. So this is the content that you need to learn to actually move on forward as a civil engineer. Okay. The content will be discussed in this lecture. There will be three main contents. Right? One is how we calculate area moment of inertia from the definition, right? And the second one, we will use what we call parallel axis theorem. We'll prove it, and then we will show the case on how to use it. And of course, the composite area, we will talk about it, and we will discuss on how we can calculate the area moment of inertia for composite area. The next one is what you should read further, right? Because this will be involved in once you get into a higher level study. It might not be so necessary at the moment, but it would enhance your understanding of the subject, and it will allow you to move forward faster when you actually need to use them later on in your study and your work. I leave it to you to read. It's in the slide as well. It's in the handout as well, I mean. Okay, before we move forward, I still want to make certain notes about what the lecture is about now. Right. Because we don't have much time, so I want to already discuss the area moment about x-axis. However, it's only the demonstration that will focus on the x-axis. But in real life, you will still need to find more than one axis, because there is also area moment of inertia about y-axis in 2D, xy axis in 2D, and then xyz axis in 3D, of course, right? So in real practice, in real calculation, we need to find, at least in 2D, the Ix and Iy usually we call area moment of inertia about x-axis and about y-axis. Right. However, because it will be used the same principle, right? But however, we will change the relevant distances. So make careful consideration when you hear the word parallel or parallel distance or perpendicular distance, 90-degree distance, something like that. This is the key word on how it actually becomes relevant in different x and y axes. So if we have an area, right, then of course, if it's in a strand shape, it's usually in theoretical when we discuss it, we not use specific shape, we just arbitrary shape we call it. So any shape, it can be any shape, right? When we talk about the whole body, we don't know the equation. When we tend to talk about a representation, in this case, a small area, dA. Right, the total area is capital A, so the representation, the small area, D mean little in front, is small in terms of calculus vocabulary, right? So small area dA. We already talked about the expression Ix, so I move it up here, Ix times y squared dA. Notice that the one that we use to actually define the arm in this case is 90 degrees to the axis we are talking about. So in this case, we talk about Ix. The measurement is y, right? So y square dA. So if IY, therefore it's the same thing. It's use the 90-degree arm, in this case x. So IY become x squared dA, and of course all IY is integration all over A, right? So again, I have to say again, think about when mention this, it's about 90-degree or parallel, right? In this case, the parallel arm is square. The polar coordinate is actually rotational about a point. In this case, it's rotate about point O, right? So the same, the distance this time, because we are talking about the movement, that is to have a point in and out of the board, or this on your screen, right? Therefore, r is the 90-degree distance, is r square. But we already know r square equal to x square plus y square. Substitute it, expand it, then we have, polar area moment of inertia. We equal to the summation of x and y, right? Notice the unit though. Okay, that's one thing that I want you to talk about. Right, don't forget that the integration is equal to summation, so the unit doesn't change on the small term. The small term is distance square, x or y or r. Distance square, so it's length square already. dA, although small, is still area. Area is also length square. So the unit of area moment of inertia will be always length to the power of 4. Okay, L to the 4th basically. Okay, so we count the unit though. So let's look at an example. Yeah, that's definition. So now how are we going to use definition with us, right? So in this first example, they set up the origin of xy at the centroid of the area. This is a rectangle. The base is b and the height is h, right? And if we determine the area moment of inertia about x-axis ix of this rectangle, right? So first, we start off, then we set up from the equation, we have ix equal to y squared dA. So we need a representation dA that has the same y all over that small dA. So of course, in this case, horizontal strip would be doing the same, right? So I draw the red strip dA. Notice the y is also the same y all over the area, right? So we can say that the small area then equal to the base, because that small strip is a rectangle, right? The base is b, and the height its position is y. The height is the small change in the y direction, so we call it dy, right? So in this case, it's b times dy, right? So we substitute into that one, and then we integrate from the lowest to the highest value of y, right, which is minus h over 2 up to the point of h over 2. Right, integrate it, substitute it, and then we have bh cubed square over 12. Okay. This is because it's ix, right? Notice that for ix is b is b power 1, but h is power 3. Okay. So let's talk a little bit, just a hint, right, on this one here. If we want to do IY, right, we'll use the same concept. We'll draw a small representation of the A, right, but this time it has to use, because it's x squared dA, so it has to be the same x on the strip, so it's a vertical strip, right? And of course the height is h, the thickness is the small change in x, so we call it dx, right? And then the whole section complete the same, right? This one here, what you should add out is h is power 1 and b is power 3 over 12, right? If you want to try, you can go ahead. So basically the idea is that the one is parallel to the axis you are looking at, right, is power 1, and the 90-degree is the power 3. Okay, so that's just a comment. There's no proof here. As I said, I will show only from the x-axis perspective. Let's move on to question 2, example 2, sorry. Right. In this one here, it's the same cross-sectional area, right? The height is h, the base is b. Right. But this time here, we have the origin x-axis and y-axis changes. Now is x is at the bottom and y is at the left side of the box, not at the centroid anymore. Right? Again, we want to find the area moment of inertia about x-axis, ix still. However, it's not at the centroid, but it's at the bottom of the rectangle. The idea is still the same, right? The calculation ix is still integration of y squared dA, right? The basic principle doesn't change, right? So we need a strip that is actually having the same y. So it's the same strip still, right? A horizontal strip, right? And the base, the whole strip, so the base is still b, and the height is small change in y, so it's b still quite dy. And the small dA, therefore, is still b times dy. However, when you put into the integration, right, because the limit change, because we move the axis, this time the limit change from y equal to 0 to y equal to h, right? So if we integrate it and substitute it, then we have bh cubed power 3 over 3 this time. Last time we have what? Let's have a look. Then the first time we did it, we have bh cubed over 12. This time, by changing axis from x is at the centroid to the base, now it's become bh cubed over 3. Then we have a problem. Why? Because if this area rotates from about different axes, we need to integrate it all the time, which is not really convenient, right? It's not like an area. You can move axis whatever, it's still b times h. That's simple, right? So we would like to have something similar to that, something that we can just calculate it rather than having to integrate it all the time, right? So we come to the next topic then. The next topic will be dealing with the case we just talked about. So we try to find an equation to solve that. If we know the area moment of inertia at the centroid, and if we want to find it from other axes, how can we do it without integration all over again? So essentially like that, right? So to use this, you have to know where the centroid is, right? And we know the area moment of inertia. In this case, we use x as an example. So we need to know the value of the area moment of inertia about x-axis that goes through centroid. In this case, we call x prime, right? An expression is there, and of course the axis, the distance between the two axes. The axis we know the area moment of inertia already, and the one that is further away from the centroid, the distance, that distance we have to know as well. So let's see how we do it, right? So here we are. We start from the expression. Again, ix is, notice that x-axis in this case is the one that is away from the centroid. X prime is the one that is at the centroid, right? So we start from the beginning equation, y squared dA, but look at how we measure, right? The distance from the A to the x-axis have to go y prime first, and then of course the distance between the two axes, in this case designate dy, not the small y though, in this case is d subscript y. Okay, so since y equal to y prime plus dy, so we have to substitute it. I said of course in square, so we can expand it, and if we expand it, then we separate into 3 terms altogether. Don't forget, integration is summation, so put plus minus can be separated into different integration, right? We do that because it can be dealt with easier. If you notice is that the first term here is equal to I by x prime already, which is the area moment of inertia about x prime axis that we already know, right? We expand the second term and the third term, right? Since dy squared, dy is a gap, that it doesn't change, it always remain the same, right? Because the distance between axes doesn't change, so we can take the last term, we can take the y squared out, right? And the middle term, we take 2 out, we take dy out, and y prime already left in the integration. So the last term is simple. Integration of dA all over A is just A, is the total area, right? So that's done. the middle term, integration of y dA, if you find that a little familiar, you should, because that is the equation we used to find centroid, right? So integration of y dA is equal to y bar integration of dA. So in this case, it's y prime, so it's y bar prime. Now the trick is here, right? Because y bar prime is the measurement of the position in comparison with the centroid, right? But this is the centroid itself, so y bar prime is at the same place, so y bar prime becomes 0. If y bar prime becomes 0, in the middle term, which are connected by multiplication, will become 0 as well. So that one disappear, and of course, then we end up with this expression here, right? The area of moment of inertia will equal to the one that goes through centroid plus the total area times the distance between the two axes to the power of 2. Notice that if it's ix, the distance we're talking here, dy, right? Because y is 90 degrees to x. Okay? We are talking again about the 90-degree arm. So if we expand it into, we do the same as y and j, then we can actually come from this expression here, right? So again, and I emphasize, if it's x, then it's dy square. If it's y, the distance will be measuring in x, so dx square. Right? So that's the summation overall. Okay, so let's see if we actually look at example 2 again, but this time we call it example 3. Right? So we're gonna find the area moment of inertia about x-axis at the bottom again, but this time we're gonna use the parallel axis theorem. Right? And we can use the knowledge we already have from example 1, which is the Ix that is going through the centroid. Right? So let's see. So this is the area, right? We already have the two expression, Ix and then the Ix that is going through the centroid. So so we have these two equations to start off with, and let's see the distance, right? So this is x prime and y prime, that is centroid, which is the middle, right? So mean that Ix bar prime is about the x-axis, x prime axis, and now we want to find Ix, right? And of course, the distance is h over 2. Again, this is Ix, the distance measured in y, right, in y direction. So here we are. We also know the area, the total area is h times b, right? A simple stat rectangle, and then we substitute everything, right? We have that from example 1, we substitute into the parallel axis theorem, and then we have the answer. Notice that this time is much quicker, much easier than setting up integration. Right? So in a way, we use the area axis theorem, a parallel axis theorem, quite often in calculation of the area moment of inertia. Which brings us to last topic, which is the composite area. Right? Let's talk about the definition. The composite area, meaning that this is an area that we don't know the shape in as a big picture. However, we can actually find a combination of two or more known areas. Right? What it means will be clearer at this time. Right? So the analysis is, first, we need to define all those component parts. And then we use area axis theorem to calculate the area moment of inertia of each part, and then we summation it, right, as for the whole. Right. So let's look at how it happened. Right. For example, this is the example we are talking about. Right. We talk about the area that is in the L shape. We don't know actually. Well, L shape kind of like laid out, right? We don't know how to calculate the area moment of inertia of this picture. However, we can view it in kind of like two rectangle shape, right? However, before we go there, apparently there are two types that we can look at, two kind of area we can look at. So let's talk about the conceptual idea first, right? From this L shape, we can look, as you're familiar with. So basically, we can separate into two smaller rectangles, right? So these are what we kind of call composite, meaning these two rectangles combined and become the shape we want, right? So we can separate into two composite areas. However, we can view it as a kind of like a big rectangle, right, and a hole, right? like that, right? You notice that the left-hand picture now is covering the height of all 40 centimeters and then the base of all 60 centimeters, right? Solid block, right? However, then we will minus whatever the hole is. In this case, the height is 30 centimeters and the base is 40 centimeters. Of course, they have their own centroid, right? In each picture that defined by the dot in middle of each rectangles. Right. So no matter what we want to do, we need to find the centroid first. So let's just try it, right? So we start from this finding the centroid. Now, before we begin, again, we already considered the area moment of inertia about x-axis. So the one that we actually want is already in the y direction, right? So I will already find y bar, right? The picture shown here, I separate into A1 and A2, right? You could use the finding centroid and finding area moment of inertia are two separate steps. So this one I use combination, but the result can be used in subtraction for the area moment of inertia later. And we in fact can find centroid using subtraction idea as well. Right. So then, right, this one I go quickly. I separate A1 and then I calculate A2, and then I have the total area, right? And put in the equation for the centroid, then we can find this position of y bar, right? As simple as that. And then we move on the next slide. Then, so once we know the position of the centroid, right, we could actually use the summation form then, right? So if you see, I also draw the axis at the centroid as well, the x and y, right? That is the total centroid in the middle. But when we calculate, if you remember the equation, bh cubed over 12, that one is actually at the local centroid, which is the area centroid that I have a dot here, right? We have A1 and A2. So we apply the parallel axis theorem into the equation. We will start from A1, right? So we substitute everything according to the distance we need to, and then of course we can calculate the area moment of inertia of x-axis for area 1. The same can be said as area 2, right? And then now it's already moved, right? Both of them, because we use parallel axis theorem already, we already move the I to the x-axis that go through the centroid. So what we do now is we just combine them, right? And then we have the answer. So if you use subtraction form, however, it will be in this form here, right? I will call it area A3 and area A4, right? Just separate from next time. The same here. We have to draw the area and then we draw the axis that we need to find the area moment of inertia about, so that we can see the gap clearly, right? As it's indicated there. So when again the same idea, we calculate for the area 3, and then we calculate for area 4. And then because it's subtraction, this is not swapping sign, right? It has to be A3 minus A4. It can't be A4 minus A3. It's a different concept. A3 minus A4, right? And here we are. And then you notice that we should have the same answer. And notice the unit. I emphasize on the unit. Okay, it's a length power of 4. Okay. So here we are. And I think that's the end of our lecture. Thank you very much for your attention, and I hope you actually enjoy and learn a lot with us. So I hope to see you guys again in the next lecture. Thank you very much. See you soon. Bye bye.